So linear momentum is the product of the mass and its velocity. Or I can say that is the product of the mass of a body and its velocity. The formula is giving us momentum is equal to the mass, which is m, times the velocity, which is v. So this is the unit for formula for linear momentum. From this formula, we can derive the units for linear momentum. For the mass is in kilogram. For the speed is in meters per second. So therefore, we can say that the units for linear momentum is kilogram meters per second. This is the units for linear momentum. So let's look at a question. It says the momentum of a body is 280 kilogram meters per second. So step one, I write out my given data. My momentum is given as 280 kilogram meters per second. And the speed of that body is 2.5. So my V is 2.5 meters per second. We are asked to find the mass of the body, m, common m. So the first thing I do here is that I will write out the equation, which is momentum is equal to mass times the velocity. Okay, now my momentum is 280, which is 280 is equal to, the mass is not given, so m, the speed is 2.5. Now to get my mass, I will have to divide both sides by 2.5. So I divide this by 2.5 and I divide this by 2.5. As you can see right here, 2.5 cancel out 2.5. So I am left with my mass is equal to, so our answer will be 112 kilogram. That is the answer, or that is the mass of the body. Let's look at conservation of linear momentum. Conservation of linear momentum. It states that the total momentum of a system is or remains the same. It states that the total momentum of a system remains the same. This means that the total momentum of a body before collision in a given direction is the same as the total momentum after collision in the same direction. So this is the conservation of linear momentum. It says that the total momentum of a body before collision is in a given direction is the same as the total momentum of the body after collision in the same direction. Now for this class, I will show us 3 different cases of how we can apply the conservation of linear momentum. I repeat that. I will show us 3 different cases of how we can apply the conservation of linear momentum to solve questions. Now, the first case here is we have 2 bodies moving in same direction with different speed after collision. As you can see right here, we have body 1, mass 1, and u1 is the initial speed of mass 1. We have a different body here, mass 2, with an initial speed. Now, as you can see right here, they are moving in the same direction. But after collision, they collide and they move their separate ways. They collide and move off with different speed. As you can see right here, the mass now have a v1, which is the final speed after collision. The second mass 2 now have a v2, which is the final speed after collision. So from this situation, we can derive a formula for it. Now, the formula is this: the momentum before collision is the same or equal to the momentum after collision. So I can say for the first situation, we have m1, u1, okay? And because they are moving in the same direction, I will have to add, okay? Then m2, u2. What next is equal to, after collision, we have m1 v1, m1 v1. Because they are moving in the same direction, I will add it plus m2 v2. So this is the equation for 2 objects that are moving in the same direction, and after collision, they continue in the same direction. Now, in case 2, as you can see right here, we have 2 objects that stick together after collision and they continue in the same direction. For example, you have a mass 1 moving with what? A speed of u1. We have a different object of mass 2 moving with what? A speed of u2. When they collide, what happens? They did not move their separate ways. No, they move in the same direction and they move as one. That means they have a what? They have a common speed, v. So therefore, I can derive my formula, which becomes the total momentum before collision must equal the momentum after collision. So I can say the formula becomes m1 u1. They are moving in the same direction, so I add plus m2 u2 equal to, now because in this case after collision the 2 objects, they move as one, so I will combine the masses, becomes m1 plus m2 times v. Remember, the v is the common velocity of the bodies because they move as one after collision. Now for the third case, it says we have 2 objects moving in opposite direction and after collision they stick together. As you can see right here, before collision they were moving in opposite direction, and when they collide they move as one. So the equation for this type of situation becomes m1 u1. Now because they are moving in opposite direction, I subtract, becomes M2, U2 equal to what? M1 plus M2 times V. Please, I want us to note that the V is the common velocity. U1 is the initial velocity of mass 1. U2 is the initial velocity of mass 2. V1 is the final velocity of mass 1, and V2 is the final velocity of mass 2. So these are the different parameters we use for linear momentum. Here we have two wagons. Our first wagon or object has a mass of 3 kg. So I can say that my M1 is equal to 3 kg. It's moving with a speed of 6 meters per second. So my U1 is 6 meters per second. It collides with another wagon of mass, which is my M2. My M2 is 18 kg. Which is what? My U2 is 0, because my mass 2 is stationary, so my U2 is 0. Now, after impact, the wagons are coupled together. We are asked to find the common velocity of the wagon, which is V. V. If you don't mind, I will draw a visual diagram. So let me call this my first mass. All right, my M1 is moving with a speed of 6 meters per second. Then I have a second mass of 18 kilogram, M2. It has no speed because it is stationary. After collision, my M1 and M2, they move as one. My M1 and my M2, they move as one. We are asked to find the common velocity V. All right. So what I do here is this. I will apply the formula. M1 is M1, U1, because they are moving in the same direction. Note that mass 2 is not moving, so it is a plus. M2, U2 equal to, now because they move as one, they are moving as one, so I will add the masses, so it's M1 plus M2 times our V. We are asked to find the common speed at which they move after the impact. So what next? I will log in the data. My M1 is 3 times U1 is 6 plus my M2 is 18, and as you can see here, our U2 is 0. equal to, my M1 is 3 plus my M2 is 18 times my V. What next is 3 times 6 is 18 plus 18 times 0 is 0 equal to 3 plus 18 is 21. We have 21 V. Okay. What next? 18 plus 0 is 18 equal to 21 V. So to get our common speed, we divide both sides by 21. So I have divide by 21. Divide by 21. So 21 cancel 21. So my V is equal to what? So my V is 0.9 meters per second. That is our final answer. Now, so our V is reduced because our mass 2 is heavier. Thank you very much. Is heavier and has a larger mass than our M1. So that impacted the speed they moved after impact. So that is our final what? Answer. Let's look at our next question. It says a body of mass 50 grams is moving with what? A velocity of what? 15 meters per second. It collides with a second body which has a mass of 25 grams and is moving with what? Velocity of what? 10 meters per second in the opposite direction. Assuming that the bodies both have the same velocity after impact, determine this common velocity. To solve this question, I will draw a diagram. It says a body of mass 50 grams. So I can draw the body of mass 50 grams. It's moving with what? A speed of what? 15 meters per second. So it's moving with a speed of 15 meters per second. Okay, it collides with a second body which has a mass of 25. So, and it's moving in the what? Opposite direction. So, is the mass of 25 moving in this direction with a speed of 10 meters per second. All right, this is 25 grams. After collision, it says, assuming that the bodies both have the same velocity after impact. That means that after collision, they move together as one. So I can say that after collision, the 50 mass grams and the 25 mass they move together as one. We are asked to find the common velocity after impact, which is V. So with this now, I can solve this question, which means is M1, U1. Because they are moving in opposite direction, I subtract. We now have M2, U2, equal to, because they move as one, I combine their masses, which is M1 plus M2 times V. So now I can log in the datas. My M1 is 50 times my U1 is 15 minus my M2 is 25 my U2 is 10 equal to my M1 is 50 plus M2 is 25 times the V. Good job. Now, when you multiply 50 and 15, you get 750 minus 250 equal to 75V. All right. So we subtract this and we get 500 equal to 75V. Now to get my V, I will divide both sides by 75. So 500 over 75 and 75V over 75. This cancel this. So therefore my V, or my common velocity, is equal to 6.7 meters per second. That is our final answer.